Hey everyone, welcome back. We are happy to have you here. This is the last workshop in this series and also the last event in this series. And we hope you enjoy the rest of the series. A couple of things before we start. Technically, like the beginner's track of this series, if you attended the in-person events, which like the live events, we didn't do any of these in person, of course, you will receive a certificate around the end of the year. So June/July, more or less. Um, we don't handle the distribution of these certificates by ourselves. It's something that Google does. So if you attended every event, technically, you should receive a form to fill in with your personal information, like name and surname, and the dates you attended these events. Um, so nothing too personal, just to put the right name on the certificate. And you should receive it around that time, so June or July of this year, of the next year, actually. So be looking forward to that, and we hope you're looking forward to our next events. We will probably send out a satisfaction form around maybe next week or in the next weeks anyway. And technically, this should be the last event for this semester. So we hope you enjoyed your stay at our DSC or GDSC experience for this semester. And now, without further ado, I'd like to invite Virginia and Jacopo again for the last time this semester, at least. We hope they'll be back soon, at least. And we will finish this event series with a boom with today's workshop. So I'm looking forward to that. I will be doing the workshop steps with you in the background, and the stage is yours.
Okay, hey everybody. So today, as Mario anticipated, we're going to be workshop, always putting our hands on Tensorflow. And we're going to be looking at something pretty cool, which is image captioning, which is quite a challenging task and not really a beginner's task, but I think it's a cool thing to start looking at some of the potentials that machine learning has, all the potential applications. But I think I wanted to start with asking if someone has revised the last class that Jacopo gave, maybe has a few questions about it, if you maybe tried rerunning the notebook, if you want any clarifications that we can give you before starting. No one has run the notebook. No one has tried running an image classifier. Appears not. Well, hopefully you're going to try it out after, maybe even this workshop. So I don't know if Jacopo, you want to add something before we start?
No, I think we're all good. So yeah, looking forward to it.
Okay, so I'll share my screen. Hopefully this time, let's make it work. Okay. Let's see. Wait, I always have technical issues with this. You need, I think, a degree to share your screen. Okay, let me try just one thing. Okay, let's see. Okay, can you see my screen? Hopefully. Okay, so let's start with brief introduction of what we're going to be doing. It's important to have a bit of a theoretical background and understand which models we're going to be working on, and then dive deep into the code. So let's start with some knowledge about image captioning. So first of all, what is image captioning? Well, I think the title is quite clear. So what we want to try to do is to produce a caption from an image. So basically, a caption is just a description. You have an image and you want to describe what's in it. And this can be done. Captions can be of a great variety. You can have a very small sentence describing the image. You can have a paragraph sentence, and that's called more paragraph captioning. So what we're going to be focusing is keep it a bit simple. So making one sentence, no more, and trying to describe what is in the image. So we're still in the domain of supervised learning. What does it mean? It means that we train a model having labeled data. So our label data, in this case, it's a bit different than before. We're going to have an image and its label will be text. So you already can see that there's going to be a few issues about this. So we don't have a fixed class like we were doing last time with image classification, but we have text. So it's going to be a bit harder maybe to evaluate. When is a caption good? Even as a human, maybe it's not quite straightforward to say when a caption is good. So we're going to have different techniques for that. But today we're going to be just looking at how we think the caption is as a human, just reading it and trying out and seeing whether it's reasonable or not, whether it makes sense looking at the picture. So let's jump on directly before looking at the notebook. Let's jump on to this slide. So because this is going to help us understand what model we're going to be using to perform this task. So you can see in this picture, in this slide, that we have a picture and a caption. So the caption is describing what we see in the picture. So the person is riding a surfboard in the ocean. What does this mean? So how does a human do this? Let's not think about a machine. So intuitively, how would a human produce a caption? Give an idea. Just try to write down where do you start from an image to describe it? Do you start from the foreground? Do you start from the background? Which are the elements? Go ahead and write it down in the chat. It's even something very basic. But as a human, intuitively, what would you do? Let's see. Try it out. Feel free to write anything, even something very stupid. So maybe starting from the foreground, colors. Yeah, exactly. We want to describe the image, and it really depends on what you want to say. Yes, as Mario said, but the context is the first thing I say. Okay, start from the center. Okay, that's interesting. We talked about colors, direction, starting where from, context. So we want to understand what do we really want to specify about the image. Relationships, yes. Relationships, foreground and colors. Very good. Okay, so all of these things are very important. As a human, you start from what is going on in the scene in a general way, and maybe then go specifying. So we said that we want to reduce our caption to one single sentence for today. So probably we want to extract all the meaningful information. Maybe what we're going to be doing is start focusing on the foreground. So here, for example, we see a person, then we see a surfboard, we see a wave, while in the background, what we see is the ocean and the sky. But as you mentioned well in the chat, it's not useful if we just enumerate all the elements that there are. It's going to be a pretty messy description. We don't really know what's going on. So we need to describe the relationship between the objects. So we have a man standing on top of a surfboard. So the act of riding, we say the word riding is important. And where? Well, in the ocean, he's surfing using a surfboard on a wave. So what have we done? So this process what we have done is we have focused our attention on the most important objects and how these are related to one another. So I'm using the word attention not casually, but the word attention, we use it because there's actually a mathematical computation called attention. So basically, it's a type of layer. Think of it like a feed-forward layer, like in a neural network, but we call it attention. So at a technical level, attention is a mathematical computation, which we're going to see even in the code, which allows us to focus our attention on different parts of an object. In this case, the object is going to be the image, but not only, also the text. Because now what we've done was the process of focusing our attention on the image and the relationship between objects within the image. But now we have to also relate these to the text. So let's do a very simple analysis of the sentence we have. The person is riding a surfboard in the ocean. Let's try to group the words. So we have the person, then which is a subject. Then we have is riding, the verb. Then we have the object, the surfboard, and then a complement of the location, which is in the ocean. And intuitively, as humans, we're mapping each group of words to an object within the image. And it's exactly what you see in the picture below. All those small pictures are actually where we focus on our attention while we're reading the sentence. So you see, some are a bit messy. Maybe they're not that intuitive. But for example, if you see person, you see some white blocks where we actually see the person within the image. So that's what we're going to be doing by code. So our machine learning model will try to relate objects of different types, which is our text and our image, and try to relate them and try to find a relationship between them. So we need to teach a model to learn to read text, but also to read images. This is the field of, it's called the multimodal machine learning. Multimodal essentially means that we're dealing with data of different types. So in this case, we have text and images. And it's quite a common task. It's used a lot in machine learning, you have to have ways of combining different inputs and trying to relate them. So we need some kind of representation for each of them. So if you look at here, these are some examples from a very famous paper, which is called Show, Attend, and Tell. So basically, this was one of the first most popular and successful works on image captioning, which is using what we have just described, the so-called attention mechanism. So what you see in these pictures is you have pairs of images, and for each pair, you have a caption. And you see that in the caption, there is a word which is highlighted. For example, the first group is frisbee. And what you see in the second image of the pair is this white, we're highlighting in white, where we find that object in the image. So this is essentially what the attention computes. The so-called attention layer computes a score for each pixel that relates the pixel to the text. So let's make a very simple example. Let's say attention is a score 0, 1. 1 if there is the object, 0 otherwise. So you see the white is 1, and it's highlighting the frisbee in the first example. So this is what we're going to be trying to implement. Actually, in our notebook, we're going to be reproducing the model which is presented in this paper, Show, Attend, and Tell. But actually, attention was first, widespread, especially in the field just of text processing. A very famous paper, if you want to take a look at it, it's called Learn to Pay Attention. And it talks about the transformers model, which is used in natural language processing, which is using attention all over the place. So there you can really get an idea of what is attention. Okay, so what do we have to do? We have attention, which is combining image and text, so relating them one with the other. But we also need a way to interpret what is in the image and then what is in the text, so separately. What we saw last time, so last time we had an image classifier. The image classifier was extracting relevant features from the image and assigning a class to that image, starting from the feature it extracted. So basically, we want to try to do the same thing because we want to describe the objects within an image. So we need to extract relevant information from all those pixels. So basically, we're going to be using, as last time, a convolutional network. In this case, in our example of today, we're going to be using the Inception model. The Inception model was built by Google. It was quite successful in the last years. It won the ImageNet competition. So it's quite good at extracting information. And what we're going to be doing is actually transfer learning, which we learned last time, which is essentially using a pre-trained network already trained on millions of data. Actually, the ImageNet, which is a data set used for the challenge, it's trained, it's a data set of more than 1 million training images and mapped to 1,000 classes. So quite big. It's already learned on a lot of data, and we're going to adapt it to our task, which is a bit smaller. Maybe we have less objects to identify. So this is for what concerns the image. So this will just use it to extract information. We're going to remove the classifier. We don't need that because it's not our goal for this task. But then we're going to be extracting information even from the text, which we're going to be looking directly in the code how to do that. And we're going to combine together information of text and image. So I understand that these are quite complex information. I'm presenting you a lot of new and complex models. So feel free to add any questions if you have any, or look it up and try to find. There's a lot of information about these models if you want to have a deeper understanding. But I'll try to give you an overview of what we're doing. So what you see in this image is a sequence model. So here it's another type of deep learning model. We talked about convolutional networks. We talked about feed-forward neural networks. So now we're talking about sequence model. As the name says, we're dealing with sequences. Sequence models were born for machine translation, which is essentially building an automatic way to translate text from one language to the other. So you have a sequence as an input and a sequence as an output. But actually, image captioning is not that far from machine translation. How do you think they are similar? In what way? How can we say they are similar? Does anyone have an idea? How can the two tasks be related? Anything, even talking about the inputs, the outputs, because we have two models that have to communicate. Okay, these are two models, but we're talking about, we want to understand how, what these models are doing. So we want to understand this sequence model. If we were using it for machine, can we use it for image captioning? So there is not just one translation. Yes, this is true. This is true both for machine translation and for image captioning, because we have things like synonyms, paraphrasing. The meaning is the same. Okay, but we should decode an image. Yes, this is very important. Exactly. Because essentially, this is a concept. The fact is that a machine does not really know how to distinguish text from images. Because what are we going to feed the machine? Well, an image, we said it's a matrix made of its pixels, and each pixel is a number, and we're feeding it to a model. But what is text? how would you translate text? So you have to understand the whole it correctly. It's the same to describe a picture. Yes, exactly. You can set a sentence into words or ideograms, okay, like in this case, but the ideograms by themselves could mean different things. Okay, exactly. We're getting the concept. How are we going to translate text? I mean, what does a machine learn? No. A machine at a very basic level knows only 0 and 1. So we're always going to have to end up there. So text is going to be somehow transformed into a sequence of 0 and 1s, as the same way as an image. So that's why we can actually use sequence modeling in the same way. So we're translating from the language of images to the language of the caption, actually. So now I think it's time to jump into the code, and then we're going to explain a few things and try to understand better how we are translating the text. So I see Mario has already shared the notebook, so feel free to start opening it. I have to change my screen. Let's see. Okay, can you see my screen? Okay, I have the issue that I opened the notebook in the same window, so I'm not going to be able to read the comments if I don't change. Well, we're gonna try anyways. But maybe if there are some questions, I'll just stop sharing quickly and then I'll read it. Or you can even speak up, or maybe Jacopo, you can stop me if you think you want me to comment a few questions. Okay, so you should already have the link to the notebook. So what we're going to be trying to do is reproduce, as I said, the model from the show, attend, and tell paper. So it's a very simple model for image captioning. You will see at the end results are not perfect, and we're going to be commenting on that. We're going to try to understand why it's not performing really well, how we can improve it. And you're going to be laughing even at some results and saying, why are we showing you this? But actually, it is a good model, and it just needs some small improvements to be able to be working correctly. So as always, as Jacopo showed you last time, you should connect here above to a hosted runtime. So we're going to be using Google's machine because we need GPUs. So what I'm showing you, this notebook, I have already run it because there are a few parts that take quite a long time. So for the purpose of the lesson, I'm going to show you already the results. But I would suggest after the lesson to go over the code, try running it yourself and trying to understand it better. Because obviously when you put your hands on the code and you actually start running it, it's when you really understand it. But unfortunately, with deep learning tasks, it's not that easy to run everything within a 1 hour 30 class because training takes time. Okay,
Virginia, to interrupt, maybe before we start, there's a question by Hossein who's asking what's the relationship between attention-based ML and image segmentation. So maybe like if you want to explain to the audience a little bit better what is the difference between what we're doing today, that is image captioning, and image segmentation, and perhaps how it's related to attention-based ML.
Okay, actually, these are two quite different tasks. So the task of image segmentation is the task of identifying in a scene, classifying each single pixel to which object it belongs to. So for example, let's look at this picture of the person riding a surfboard. So in the task, let's say, so image segmentation is essentially equivalent to the task of giving a label to each pixel in the image. So for example, what we want to do is identify the main objects, which is the person, the surfboard, and let's say the ocean and the sky, to be very simple. So what we're going to end up is that every single pixel in the image will be marked as belonging to the sky, the ocean, the person, and the surfboard. So this is basically image classification. You don't need any attention. Although now there are more sophisticated models, not really sure, but I probably, if you look it up, there probably is some attempt of using attention for image segmentation. But you usually use some different models, which are have a quite complex architecture, but you usually don't use attention for because this is basically a task of image classification. Instead, image captioning, you have to relate objects you identify. You not only have to identify objects like in image segmentation, but you have to relate them. So that's the most important part. So it's not sufficient to say that in these pixels you have a person and these others you have a surfboard. You need to understand what is the relationship between them. In this case, the person is riding a surfboard, and then you produce text based on it. So that's, I think, the difference that you're looking for, the fact that we're relating objects with one another. But very interesting question. Now, I do not know of any specific model using the attention for segmentation, but probably there's some attempt. Now, today you can find models for images used for text, vice versa, and for any task. So I'm guessing there could be some kind of model for that. Did I answer your question? Is it... did I get the point?
I think it was a good explanation.
Sorry for that loop. Okay.
Yeah.
Yeah, I really need I need a degree on sharing screens. All right, so let's jump directly to the code. We already saw that example. So first part, we're downloading all our libraries. Okay, let's
Virginia,
go to...
Can I suggest you something so that maybe we can see the screen better? If you can please close like the left and right windows, and then so that it will be a bit bigger. I think this will be helpful.
Yeah, you're right.
Yeah.
Let me know. Do you want me to zoom maybe?
Maybe just a bit. Yeah, I think that works. Yeah, this is perfect.
Great. All right, thanks, Jacopo. Okay, so first part, actually, question. What is the process that we're going to be following? So what are the basic steps that we need to be doing from now on in the whole notebook? So think of the exercise you've done last time. So the image captioning, image classification. Think about all the pipeline of steps that you were doing one after the other, and try to understand what we need to do even for image captioning. So go ahead and try out. I'll have to open here. Obviously, you're going to see a loop. Anyone has any idea of the pipeline? So, for example, I'll give you the first task, and then you can continue from that. Data collection. So we need to collect the data. Okay, Anastasia said libraries. Okay, load data plus augmentation. Okay, already more complex. Build the model, train the model. This is good. Let's try to, test the model. Okay, great. I think we're needing one step extra. Verify test set, train test split. Okay, we're getting in that direction. Improve the model, sure. Let's think more about, I think we mentioned a few times, Jacopo and I, that we spend most of our time in our job on the data. Let's say 80% of our time on the data. Maybe we need to do a bit more than loading and augmenting. Let's see, anyone? Even very general. Clean the data. Okay. Preprocessing, yes. Scaling, yes. Good things. Yes, we have some raw data. maybe in this case, we're going to be using a popular data set, which is the Cocoa data set from Microsoft. So pretty reliable. But once we have our data, we can't just feed it to the model right away. We need to a bit process it and make it feasible to be accepted by the model. And also interesting, the fact of data augmentation, I think this will be an interesting topic because we're going to be, how do we do data augmentation with text and images? So that's going to be an interesting question, but maybe we'll keep it for later. Okay, so let's go on. So the steps are those, exactly. Let's start from the data set. I said we're going to be using the Cocoa data set, which is a popular data set from Microsoft. It has more than 80,000 images. And for each image, we have more or less 5 captions. So why is this? This is because, as you said, some of you mentioned, we don't have a unique translation. We could be using synonyms, paraphrasing, restructuring the sentence. So why are we giving 5 different examples? Well, it's to help the model learn that there is not one unique way of describing an image. There are multiple ways. So we kind of have to teach our model that synonym exists, that, for example, if you write a sentence in an active version or passive version, it means the same thing. So all of these things we need to teach our model because it doesn't know from zero. Unless, well, we are using even a bit of transfer learning. So it's not going to learn from 0. Anyways, this code, very fancy code just to download the dataset. And once we have our dataset, so we're not going to be using all of it. You're going to see that when you're running this dataset, probably your notebook is going to crash a bit, or like mine did, or if you haven't cleaned up the cache, because the dataset is heavy. We're going to be using a smaller part of it, which just for the purpose of learning. Obviously, the more data you have, the better. And if you have enough resources, use them. But for sure, training on more data means you need more training time. So you're going to wait longer time for your epochs to run, longer time to do hyperparameter optimization, but then better results. So it's always a trade-off, even in the industry, even when you're working for a big company. Not necessarily, you have resources, but not necessarily you're going to use all the data you have, because sometimes it's just not feasible. You have to wait too long. And maybe it's not even worth it. Maybe you get to a desired level of accuracy without all your data sets. So you start small, reasonably small, and then maybe improve if you need it. So what we're doing here is essentially we're trying to get a subset of these images of the data set. So we're going to pull 30,000 captions, which actually, as we said, for each image, we have around 5 different captions. So 30,000 caption means they correspond to more or less 6,000 images. So we'll keep our data set limited to that. Okay, let's start looking at an example. So this is one simple example of the data set that describes the picture: an orange and white train traveling past a forest filled with lots of green trees. So we see it's not really a too simple sentence. It's describing quite clearly all the objects in the scene, how are they related to one another, and also the colors. So we're going to try to do that with our model. And then what you see as well is 2 special symbols within the text, which is the start token and the end token. I call them token because this is a process we're going to be taking up on to elaborate, to interpret our text, which is the tokenization. Let's give it a go. Try to tell me, in your opinion, what is tokenization? So I just already anticipated that is how we want to translate our text, but try to say in your own words what you think it is, and how would you go from there on to interpret text. So let's talk about manipulating the text. Try out, giving some ideas. It's missing the water, you're saying in the image. Yes, true. If we had maybe a longer sentence, we could add it. Why not? It really depends on the scope, on how you want to restrict your captions. So a token, a work, maybe? What do you mean by a work? Tokens equals tags like noun, verb. Okay. Word. Okay, word. Okay, yeah, exactly. A token equals a word. Not necessarily. So what Mario said, the token about noun, verb, that is true in another context, the context of, it's called part of speech tagging. It's actually a very common task in natural language processing where you're automatically labeling text as saying whether it is noun, verb, etc. In our case, we're not doing that. In our case, Anastasia is correct, and we're assigning GPT-3 stuff. True. Well, not really. Almost. So a token, in this case, very simple case, is going to be a word. So our vocabulary essentially has the size of the number of tokens we're assigning, which is the number of words. So let's say the article the is the token 1. Then we have the word train is the token 2, and so on. Then there are, we're going to see in this simple case, then there are more elaborate tokenization methods. So you mentioned, Mario, GPT-3, which is a very popular now model for text processing, where text is elaborated in a bit different ways. So mostly your tokens are both words and parts of words, like syllables. And this is because there are some issues. For example, what do you do with an unknown word? Let's see, try to reply. How would you deal with a word that you don't have in your vocabulary? How do you deal with that? Any ideas? So we said we have a fixed vocabulary. In our example, we're going to be using a vocabulary of 5,000 words, if I'm not wrong. But what happens if you find a word that is not in your vocabulary? How would you do it? Any ideas? Anything? Try out. To compare. Okay. How? How can you compare a word to another? So we're guessing like synonyms. So find the closest word in the vocabulary. Okay, interesting. Even in that case, how do you find the closest word? What does it mean, closest? Discard it completely. Other option, totally doable. See where it's used. Yes, we're getting there, understanding the context, which is something that our model is going to be learning, because we are going to be learning the context of the sentence and maybe learn what is a synonym based on the context. So you were talking about similarity. Similarity will be maybe similar context. So all the similar words around it. Wow, Levenstein distance. Interesting. Something like generating new words. How do you say to a machine to generate a new word? I mean, maybe there are. I'm not doubting that maybe now there are, but usually a machine is not really that good at generating something new. It's better at learning what it's told to. So essentially, so for example, one way that GPT-3 is using to deal with new words is that it's splitting a word into its components, maybe a prefix and a suffix. And you're learning maybe that a prefix is used in different contexts or has a specific meaning. A suffix has another meaning. For example, in Italian, the adverbs all end in mente, so they're all ending in the same way. So the machine is already learning that. But also, as all of you said, the main way of dealing with rare words is looking at the context. So that is what we're going to be trying to do. But if the machine doesn't know what to put, or if it doesn't know a word, in the training process, it will assign the label unknown, we can do even a very simple thing like that. It's the same thing as you said of discarding a word, placing the token unknown and not even dealing with it. Okay, so let's move on. So we collected the data. Now we move to the step of processing the data. We have two types of data. We said we have the images and the text. Let's focus on the image before. And it's essentially what we saw before in the slides and the same process that we dealt with for image classification. We need some model to extract relevant information from an image. And what we said is that we can take advantage of transfer learning, which is essentially using a pre-trained network, which was trained on lots and lots of data, and use it for our use case. So we're going to be using Inception v3, which is basically a model. It's a model from Google. Model, but we're not really interested in on all the complex architecture of it. We're getting the pre-trained one, and we're feeding it with an image, and we're extracting relevant information, which is essentially getting the output of the last layer before the classification part. But why is this? Because we said that we want to identify objects in an image and relate them. So the part of relating, we're going to be using attention, as we said. But how can a classifier tell us which objects are in the image? Well, exactly that. We're trying to classify the image. And we can use, there is the multi-label classification. So we're assigning multiple labels corresponding on the different objects we find. So that is why we can use a pre-trained model for image classification and use it for our task, even though we're not doing that task. So basically, we're going to be using Inception v3, trained on ImageNet, which we know is able to recognize 1,000 objects because it's trained on 1,000 classes. So more or less, it's going to be sufficient for our task. So what are we going to do? Let's load the image. So this is a very simple function, which is trying to pre-process the image to be able to Inception v3. And actually, we see already there is a function within Keras, which is pre-process input, and it's specific to different architectures, because Inception v3 maybe wants some kind of normalization of the pixels or some other kind of manipulation of the pixels. We're not really interested. We have a function that does it, so let's just use it. Okay. And then let's load Inception v3 as it is. We feed it with the image that we pre-processed, and we extract the output. We say, if you see in this line, the Inception v3, we say include top equals to false, because we don't want the last layer of classification. We're not interested in getting a classification. We just want the layer right before it, which is all the, let's call it an embedding of the image, which is a kind of condensed meaning of the image. And we're going to be using that to feed it to then the attention. Okay. So now this is a step which will take you, well, no, okay, it took 1 minute, really long. It took more to collect the data. As you can read here, this is caching the features extracted from Inception v3s. This is something you don't normally do. What it's doing is basically it's storing all the image already pre-processed. Pre-processed means passing it through Inception v3. But that is for simplicity for us to train a bit faster. But usually when you're doing this exercise in a standard way, you will do it on the fly when you're training. You will pass it through Inception and then through the other layers of training. But here we're doing it for simplicity. Also, it occupies a bit of memory, but it's fine. We do have it right now. So you can take a look at this code, but essentially we're just caching. Okay, now let's move on to the processing of the text. So here we see all the sequences. Oh, oops, it's getting crazy. Oops. Okay, don't know what happened. So let's go over the steps and try to explain the code. We're going to be doing what we essentially said before. We have to pre-process the text so that it can be read by a machine. So first, tokenization step. We said it before. We use this object from Keras called Tokenizer, which essentially maps from each word token, which is, for example, giving it an identifier, 1, 2, 3, X. And here we're limiting the vocabulary to 5,000. So this step we do because otherwise, if we have to learn a huge vocabulary, it's going to be taking a lot longer. It's a lot more complex network. Sure, maybe we're going to get a better accuracy, not necessarily enough accuracy, so we don't need it. If you think standard net GPT-2, for example, of 50,000 words or subwords. So, but we don't really need anything too sophisticated to be learning. But then, of course, if you want to build a more robust system, maybe you're going to need a bigger vocabulary. Okay, here, what you see in this line, you're filtering special symbols. And you're defining the unknown token, which is what we said before for words you have never seen. And you're filtering out all these symbols because you're not mapping them to a specific token. Okay, and then there is a fit. Okay, and you're trying to fit it on your trained caption. Every token, you're using this tokenizer to tokenize all the caption. This is essentially the process. So what do we have here in this code block 14? We're doing padding. Padding is an operation which consists in adding this special token that in this case we call pad. Remember, you can use you want. For a machine, it's the same thing. And this is to get tokens of the captions of the same length, because to feed a machine, it's always expecting a same sized input. So even if we get shorter captions or longer ones, we want to feed everything of the same size. Okay, so here we have another processing step, but we're calculating the maximum length, but these are just pre-processing steps. Overall, the concept you need to learn is the tokenization and the padding. Okay, next step. So we're getting to the end of the pre-processing, and then I want to stop a bit to understand about data augmentation, because I think it's quite interesting, especially for text. Here, a bit of a fancy code again to split our data into training, validation. Here we're not doing testing, but it's actually this validation set. But it's in this notebook is being used for testing. Otherwise, the validation should be used during the training to perform validation, for example, through early stopping or other techniques. And then you need a different test set, which you've never seen before, to try out your model. So this is just doing that, very standard size training and 20% validation. Usually these are the ranges, maybe 70, 30. If you have very small data, you want to try to use it as much as you can for training. So maybe do 90 and 10, but you don't want to risk overfitting. That is always a big trade-off. If you use more training data, then you risk overfitting. But there are other ways, for example, tweaking the loss function, the learning rate, to help you mitigate this problem. So there are other solutions, but we're not going to dive too deep into it. Okay, so last step before we jump into the model, here this is just configuring the data to be ready for training. So we're grouping the data in batches. So what does it mean? So in our training step, we're learning a batch at a time. It's the same thing we did even last time with image captioning. So essentially, you're learning gradually to update the weights in your model by learning from a batch of data at a time. So we're essentially doing that function. And these are some very just fancy code to essentially say that we're grouping the data in batches and we're separating it in order to be dealt in parallel between CPU and GPU. But this is done then in a transparent way by TensorFlow. So you need parallelization. Okay. Before building our model, I think we can talk about data augmentation, because if you already know you have a small data set, in our case, we're just using it smaller. We could have a bigger size data set, but what would you do for data augmentation? Let's try to remember what we did for images last time. Try to do something that includes even text. Let's see, share your ideas, anything. Oop, have a loop here as well. Okay, something like generating new words. Oh no, sorry, this was this was for before. Go ahead, say your ideas. Another language. Then you need a model to recognize that language, though, right? Flip words. Okay, what do you mean by flip words? You mean exchanging words in a sentence, or flipping the word, so changing its characters? In a sentence. Okay, yeah, this is a solution. It's called a random, let's say random swap of words. This is done. Let's say it's like some kind of form of introducing noise in the sentence by flipping, so swapping essentially two words, and it's done. This is one of the techniques. Go ahead, try out others. Changing one or two characters in a word. Okay, could be done. Let's see, something else. Lower and uppercase is just managed. Usually it depends on the embedding you're using. So it depends on the model you're using to interpret text. There are models which deal with lower everything lowercase, so they don't deal with case, or they are case sensitive. So, but that's not really. Let's think of, we're in the domain of we're not case sensitive. Try to think about, even as a human, how would you produce similar examples? Okay, use synonyms. Yes, this is good. Anything else? Any idea? Intuitively, really, just try it out. Even because there are many techniques adopted, and some are even quite weird, but nothing else. Yeah, these are all good examples. Synonyms for sure. How could you implement paraphrasing? So let's say producing the same, let's say your goal is trying to build a sentence which is similar in meaning, and actually the same in meaning, but it has a bit of a different structure. How could you do it in an automatic way besides using synonyms? Because one thing interesting you mentioned is another language. Because if you think of how sentences are structured in different languages, you see sometimes they do have a different structure, but they mean the same thing. Passive active voice, yes. Using definition of a word, okay, could be. There are many things you could be doing, and you could get creative about it. One cool thing that is done is, for example, using models for machine translation. So you translate a sentence to a different language, and then you translate it back. Because sometimes, actually many times, that model is going to be translating the sentence in a different way. So you're going to get the same exact meaning, but in a different way. Every sentence has an embedding. Maybe if two sentences have similar embeddings, they mean the same thing. Yeah, true. You need a model for a sentence embedding, and you can try to understand in the space of the sentences if there is a similar one. Everything true. Actually, you can get really creative as well as for data augmentation. You could even keep the same caption while changing the image. So maybe you're flipping it, maybe not changing it too much so that the caption doesn't match anymore. For example, if you're changing the colors of the image and you're talking about a yellow train, then maybe it's not going to make sense anymore. But yeah, these are all great ideas. In the domain of data augmentation, you can really get creative. There's no one unique way or standard way. Okay, let's move on to the model. So here as well, it's the decoder below is identical to the one of the example of neural machine translation. As we said before, we're doing the same thing of machine translation. So what are the components we need? So this first block of code, you see it's called attention. This is essentially the attention mechanism. These, you can go ahead and look at layer by layer what it's doing, but let's get a bigger, a better idea. So how do we relate? Okay, question. What mathematical operation, like division, sum, or something like that, a mathematical operation, what would you use to relate two vectors, to say that one vector is similar to the other? What operation allows you to do that, to build similarities? For example, let's say you have vectors of ones and zeros. You want to sum up all the ones which are matching, and then where the zero, there you see you have no matching. Do you have any idea which operation you could be using? So it's basically telling you if there is a correspondence, one in a one, or if there is no correspondence, a one and a zero. How would you take into account? Scalar product. Yeah, we're talking about dot product, essentially, multiplication. That is going to tell you whether two objects are related or not. Very simple. And this is doing a bit more steps, but essentially when you're doing dot product is when you want to relate two vectors. This is just adding a bit more layers to learn it, but the concept did this. So then what we want to build is a sequence-to-sequence model. A sequence-to-sequence model that we saw at the beginning has two components, which are an encoder and a decoder. So the encoder is encoding information. What does it mean? It's interpreting information. And the decoder is translating that information. So we're interpreting, in our case, an image, and we're translating it into text. So our encoder is going to be the image processor, and the decoder will combine the image and our label, which is the text, and learning to produce that label. So learning to produce a sequence of text. So what we have here in this block of code, we're building an encoder. Here, very simple way, we're building, as you see here, a dense layer, which is a feed-forward neural network. This is because we have already, if you remember in the code above, passed the image through the inception network. So we have already extracted all the information from the image. And now we just want to use this image and resize it, learn it, resize it to an embedding dimension which we specify, which is going to be used to combine it with the text. We need a same size to combine the two. And then last step of the model is the decoder. We said we have these two components. So the decoder has to receive two things, the image and the text. And the text, the text, we already tokenized it and did padding. Now that every word is a token, which is, let's say, a number, we don't really want just an identifier like a number. We want a better way of translating the text. We want to extract meaning. Because if you think of synonyms, let's say similar words, vehicle and then car. You want to somehow understand that these are similar concepts, right? So we can't just say that one is token 100 and the other is token 200. How do we really relate them? We want to find a numerical value that understands about the similarity, and that is called embedding. So this is a layer from Keras, which you learn. So you learn to translate all these tokens into into a vector of numbers, which encodes information also on the semantics of the word. This is a simple case. What is done today is to use more sophisticated pre-trained network, the same concept of transfer learning, and you use GPT-2, GPT-3, BERT, depending on your scenario. But same thing. We're just doing it simply and a very simple. And what you're passing it through is to this gated recurrent unit, this GRU, which is basically what you saw in the slides of, let's see, we have it here. Nope. If you can see here, the sequence modeling, these blocks are the gated recurrent units. And here, sorry, these green ones. And basically these are networks with a feedback loop. You're passing it one token after the other of the text because we want to interpret a sequence and produce a sequence. So, that is what we're doing with the GRU. The GRU is just a recurrent unit. And then we're putting everything together. At the end, we're adding dense layers, and then these are just to resize the embeddings. And then we're learning, we have the attention, which is how we combine the embeddings of the images and the text. And here in the call function, this is where you define all the different steps. So you're passing from one layer to the other. So this is essentially what we're going to be adding. So you can read here, but this is basically all the combination of the steps that we have discussed before. And then you plot out what you want, because it's interesting to plot them. Once you have them, we're going to be seeing all the visuals that we saw in the examples. Okay, so before actually running the training, what do we have to define? As usual, we need a loss function using last time Atom. So this is how we're going to update an Atom as a quite sophisticated computation, but it's basically adapting your learning rate. But it's a bit more complex than that, but let's take it as is. It's working well. We're going to use it. And sparse categorical cross entropy is a type of loss function for, it's used for when you have different classes. But let's say we're going to be using this, take it as is, but you can go read about it. It's but in this case, we're going to be using this. Okay. And here, just this is the check. How do you store a model when you're performing training? And then we're going to run to the training steps. So here, a bit more details before actually seeing the results. So we said we're running supervised learning. So in the case of image classification, you feed an image and its class associated to it, its label. When we're doing image captioning, we're feeding an image and a sentence, which is a sequence of tokens. It's feeding one token at a time, because we said that we have a model. So we're feeding one token, we're learning, and produce the next one. Then we're feeding the second token, and then the third one, and so on. So during the training step, we feed the real exact tokens, so the real ones from the caption we have in our labeled dataset, to the model. So let's say the image at the beginning, it was, let's say, a man on a surfboard. Very simple. We feed each training step we feed a, then we feed a man, then a man on, then again a man on a surfboard. That's it. And the model will learn, for example, from a man, maybe it's going to make a mistake. It's going to be saying a man is, and maybe want a man on. So at the next step, we're going to feed it with the right word. We're not going to be feeding it with what the model said. So this is called the teacher forcing. And I recognize these are a lot of concepts. Take it as is. Think of it as a teacher who is forcing a student to learn. It's gradually helping it step by step. And that's what we're going to be doing, what we are doing with the model. We're helping it step by step to build a meaningful sentence. And this is what is actually coded here in this code block. Next code block, we're actually performing the training step. Here we're doing, this is very arbitrary, 20 epochs. As we said, the ideal way should be using early stopping or trying out different epochs. Not necessarily this is the best way. We always have to take into account overfitting. But let's do it for simplicity like this. And here we have all our results. Here it's computing the loss on each batch and then the final loss. See that it's averaging it out, basically. And here we're reducing the loss at each step. Okay, hopefully it's not going to overfit, but we'll see the results. Let's see if I can close this. No, it's not going to be closed. Okay. Let's look at the plots, and then I think we can move on to reasoning together a bit about the results. So here we're plotting the training loss, which it should be like this, so it should be decreasing. It shouldn't be many, there could be some errors in the meantime. It could increase at some point, but then it's going to go normally decreasing if we didn't do anything weird. Let's evaluate. So evaluation is done in the same way as training. But we're not using teacher forcing anymore. So we're not guiding the model through what is the right caption, but we're letting it produce the caption. So it's going to produce one token at a time and keep refeeding itself with the last token it produced. It's going to produce then it's a man on a surfboard. So this, if you see it step by step, we're basically rerunning the same things we were doing for training, without teacher forcing. Same thing. You're starting from a start token because that's your starting point. And then the model learns to reach the end of a sentence and place this end token. Because this is what we taught him, because we gave him training samples with this. So it should be learning to place the end at the end of the sentence. Here we're writing a function to plot the attention, because as you remember before, we are returning the attention as one of the outputs. So we have it and we're just plotting it out. This is basically resizing and putting in a way where we can actually see it decent and having good results. Okay, let's look at this. Well, let's look at one example. Actually, here you can't really see, I don't know if you see it well, but I don't really see the image that much, but it looks like a bunch of people. What is it saying? The real caption, let's read. She's talking on her cell phone next to luggage while another looks on. Okay, this is cut because if you remember, we set a fixed size of the caption. So we stopped it there because probably the majority of captions were shorter. And let's see the predicted caption. People are waiting and with luggage indoors. Not the best result, but it's getting some concept, like people and luggage, and they could be waiting. I mean, apparently they could. Let's see if we want to try out a different example. Let's see. A man with, these examples are very small. I don't know if you can see it. Very small over here. And the real caption is a man with a tennis racket bends it behind his shoulder. Okay. A woman steps down hitting Cajun ball. Wow, this is really bad. Let's try another example to see if it's going a bit better. And remember that this example is from Google. So a wooden cutting board topped with 2 sandwiches, a fork is prepared on a table. We're getting the concept of food and table, but we're not really getting there. And here below, you can even try your own images and see how it works. And I think what we can do now is focus a bit on the results. Why do we have such bad results? I mean, it's not too bad. It's learning some concepts, some concept of people, some associations, but no, they're not really the best ones. So let's try another one just to see. A train, oops, why is it doing this? A train traveling down train tracks, forest, train along the tracks for a commuter train tracks. A lot better. It's improving. So now, ideas. Why is it bad? Okay, sorry, but we teach our AI to connect small elements of an image to a number of word or each word to small images. You're saying, let's see if to connect a small element of an image to a number of words or each word. Actually, you don't have to see it as one way. So you're connecting one part of an image to a word or group of words or vice versa. Because you're doing the process in parallel. You're learning to relate objects. So multiple objects from the text to multiple objects from the image. So you're learning it, you're not forcing the relationship to be from one object to one word or multiple words. So it's going both ways. So anyone has ideas of how we can improve our model? Why it's doing like that? How do you improve it? Very simple way, maybe. Think about the data we used. Well, one thing we mentioned already, which we haven't done in the code, is data augmentation. That could be helpful. But before that, before using synthetic data, we need maybe the whole data set. We remember that we reduced it to 30,000 captions, which is 6,000 images. So let's see. For example, delete the article, a word not important. Well, we can delete the article, but then we're not going to get human readable sentence. We want, as humans, to get a good description of the sentence. We don't want just to understand what objects are in the scene or the relationship, like person, surfboard, riding. That already tells us what's in it. If we want, it all depends on our use case. If we really just want to capture objects and relationship, we can even do it like that, very simple. But if we want something a bit more elaborate, we meaningful text where you have both correct semantics and syntactics, then articles are important. But any other ideas on how to improve the model? So we said we didn't use all the data sets, so probably using the full data set can help. Data augmentation, and then think about how we trained it. What were you missing? I think we even mentioned it. Any ideas? Increase the number of training epochs. What is the risk there? What happens if we increase a lot the training epochs? Does anyone know? What's the risk? Could be useful, but yeah, exactly, overfitting. So how do we prevent overfitting? How do we know which is a good number of epochs? Change the model or the neural network used? Okay, maybe which part though? Because for the image, I think we have a pretty good model, the Inception v3. I think I won enough awards to extract meaningful information from the image. Maybe we can focus on the text. The length of the caption, maybe. Yeah, as well, could be. Sure, the smaller the caption, the easier it will be for the model to learn, although the less details we have to learn. The longer the caption, the more data we will need to be able to learn such a complex sentence, but it could have more information from which to learn. So it's all a bit of a trade-off. So to reply briefly to the overfitting, we would use early stopping, which is a technique which involves using a validation set. As we said, validation set, what you're doing is at each epoch, at the end of each epoch, you evaluate your model on the validation data. And you keep going, you keep training until the validation loss starts increasing. So I'll show you a very quick example. If we look at early stopping, I think we mentioned it last time, but look at these examples. Let's look at this curve. You see the training loss always goes down in training because we're learning from the training set, while the validation set, we're not learning from it, we're just evaluating it. So at the beginning, we're learning the problem, so we're learning it at some point, but at some point you see the loss increases, and that's the point where you stop generalizing, you stop being able to generalize, and you start learning the noise within the data. Because there's no perfect data, there's always going to be noise. But yeah, I think you mentioned a lot of great things. So you mentioned about changing the model. What we could do is use transfer learning for text. So as I said, instead of using that embedding layer, we could be using an embedding extracted from, let's say, GPT-2, or even a more simple one, a BERT, a small BERT. Okay, any other ideas you want to pull out to improve? I mean, these are already great. Focus on the data, getting more data. So data augmentation, getting the full data set, improving the model. Sure, we built a small model. It could still work. I'm more of the theory of improving your data rather than improving your model. Okay, and obviously in the length of the caption, all of these are important. Another restriction we made was the vocabulary. If you remember, we used only 5,000 tokens. We might need a bigger vocabulary to learn from. No other ideas? Oh, so I missed okay, what about the color? Okay, well, color, we don't. Okay, let's think of it in this way. In the classification task, the color was important, right? But we never told the model about the color. Sure, for the first example that we did was on the fashion dataset, which was black and white. But on the transfer learning example, we used, I think we used colored images, if I'm not wrong. The concept is that we're already giving the information about the color to the model because we're using RGB images, which means that each image is a matrix with, so it has 3 dimension, and the third dimension is that of color. So each pixel is going to incorporate information about the color as well. So we don't even need to say it to the model. So a different training algorithm, maybe not so linear as the next word approach. Okay. Could be, but yeah. Here's not necessarily learning to correct the next word, because that's the next word. We're feeding it increasingly with a longer word. So it's getting a bigger and bigger context. But yeah, I get your, I think you're getting there. And if you try to look at models like transformers, like GPT-2, what you see is that they don't learn sequentially. They learn getting all the text at once, and they use attention to look at the relationship between objects. Okay, I think if you don't have any other ideas, no one else. Okay, I think we wrapped up this. We don't have anything else here in the notebook. Here you can, there's a function where you can try out your own images if you want to, if you build a captioning model and you want to try out the images you have. Or here, last thing you can take a look at, it suggests looking at machine translation, which is another very useful task. And you will see that it's essentially you build it in the same exact way as an image captioning model. So this is essentially for you to get an idea that we're not just learning image captioning because we want to just learn how to get text from an image, but it's more of an abstraction of many different tasks you could be working on. But yeah, I think that stops it. I'll stop sharing because I think this sharing part was the worst. Not really good at it. I'll try to improve for next workshops. But yeah, I think we still have 9 minutes, so I guess we can move on to Q&A. If you have any questions about the exercise itself or more in general to Jacopo and I about anything. I think this is the wrap-up lesson of the workshop, so go ahead and ask us.
Yeah, I think first let me say that was great. Very interesting to see how we move from image classification to image captioning and the differences. I think that was quite great. So I would also ask the same question that I asked just 2 days ago. How helpful you think this was for you? I wanted to, in the meantime, answer. I think it was Mario asking about hardware. Ideally, what hardware would you need to handle this stuff in a timely manner? I don't think we answered this question, right? So the whole point here about hardware is that nowadays hardware that's used for machine learning is usually in the cloud, and only a few people would know how that is built with which components that hardware uses. And so when you launch jobs where you train your models, you can choose on the cloud, you can choose the instance type with which you want your models to be trained. And so you may choose a memory optimized instance, or more like a GPU optimized instance, or something that uses the disk for some reason when you're dealing with a lot of data, and so you would need a lot of memory, but there's no way that you can use a lot of memory. Then a way to train your model would be that of also leveraging your disk. And yeah, then of course there's distributed training also. And so it's like professional hardware that as a scientist you don't want to really bother about.
As Mario said, thing is essentially done AWS cloud, Google Cloud. Yeah, it's true because it's not worth it. It depends on the task, but most of the times it's not worth it to buy your own machinery because maybe you're gonna use it for some time and then you're gonna leave it there. While when you're using cloud computation, you're using some machines which are always being used by even other users, so that's gonna lower your cost. But yeah, and also, I mean, for some of these tasks, you need multiple GPUs in parallel. Jacopo said a lot of RAM, especially RAM, not only disk, but otherwise everything crashes. Or there are techniques, obviously, to mitigate these. You train in mini batches, but then you're always trying to reduce way of training. But but essentially the best way is just doing it in the cloud. And for experimentation purposes, the great thing is you have things like Google Colab or Kaggle that provide you some free GPUs. Be aware that they go in idle after some time, so don't use it on your thesis.
Many of these services have free tiers. So that means that for a certain amount of resources, a certain amount of period, you would get free credit. And so you can definitely go ahead and consider those options to develop like a personal project or university project or your thesis without paying a lot of money, if any. So yeah. So Google Cloud, AWS, Azure, they all have free tier, but there are also many other cloud providers that are minor but still used. All right. Well, then it seems like there are no specific questions, but of course we'll be available anytime, and feel free to ask any other questions in the Telegram chat and on the other social media. I'm sure Mario will now close off the session with some closing words and invite you to follow all the other events. Maybe we have a last question we can answer by Filippo. So Filippo is asking us, do you think that quantum computing will soon help us speed up our machine learning training? It's a super interesting question. And actually, let's clarify that there is indeed quantum computing research that's already being done in big companies as well as important research institutes. And quantum computing is non-deterministic. That's also one of the issues of quantum computing. I don't know much about it, but as far as I know, it is non-deterministic. And so that would mean that when you do, as far as I know, again, please correct me if I'm wrong, but if you do 2 plus 2 plus 2, then it will be equal to 4 only like 98 times out of 100. And so you would say, okay, it's equal to 4. But to be honest, I would say yes, but I don't know how soon that soon is. So that's my answer. I don't know if Virginia has a different take on this.
Not an expert, for sure. I know there is a lot of work trying to adapt deep learning being run on quantum computers. It could potentially benefit a lot for training, speed up training very much. But yeah, it has its own problems and risks. Although I'm not an expert, so I'm not really sure how far we are from achieving it. It's not going to be that short term for sure. Bits are called qubits. Yeah. Same, very very little idea. I'd like a computer that tells me the right answer. One. I want to be sure about the answer.
Okay, so I was having a little bit of a problem with the webcam. So yeah, well, I'd say this was extremely interesting, very educative, very entertaining, and so I would like to thank you both for coming for the past 2 weeks. And I'd say we can wrap this up. You will find the recordings on YouTube maybe in a couple of days. It just needs to wrap up the event, render the stuff, and then we'll upload it to our channel. You can find everything in the link that I pinned in the chat. So Instagram, the Telegram group, our Discord server. Follow us for the next events that we're gonna make, probably starting next semester. And yeah, thank you all for coming. Thank you to Virginia and Jacopo for being our facilitators again for 2 years in a row. And yeah, so have a nice evening, and we'll see you again next semester.
All right,
Bye,
thank you.
everyone, for attending. Bye.